So, welcome to this last talk of the second week. So, what are we going to learn today in this talk? So, we are going to learn today about chain rules. Chain rules are important when you compose two functions, that is you take an element and get it to one set, and on that new set you put in another function, you employ on the image, you employ another function to get another element. So you use two functions one after another, and that is called a composition of functions. In a very abstract setting, for example, if you have three sets, I assume that you guys have some idea what sets are, because I am using, you have learned, we have used sets freely in one variable. So here I have an x and I have a function f mapping me to some point fx here, and then there is a function g, so which takes me to a point, and this point is g of fx. So if I write this function h as g composed f, that is first I apply f, then I apply g. So f followed by g. So this, so h of x, which you can write as g composed f of x, is nothing but g of fx. So if f is carrying an element from a to b and g is carrying an element from b to c, then h, which is g composed f, is carrying an element from a to c. Now how would you handle, suppose we are talking, these are sets in real line, this could be a closed interval or open interval, and this is the real line and this is the real line. Then we will be talking about sets, we will be talking about functions on the real line, composition of functions on the real line. For example, if I talk about a function like this, y is equal to sine of x cube. So if you observe, I can put f is equal to x cube and g is equal to sine of say z. Then what I am doing, f is giving me x cube, f of x is giving me x cube. So f of x is x cube, and then I am applying g of f. So y can be actually written as g composed of f. Now if I look at this function f equal to y is equal to sine of x cube, then y equal to sine of x cube, this function is differentiable. Y equal to sine of x cube, the sine function is differentiable. So here my f is differentiable, and here this f, this function is differentiable, and this g is also differentiable. So both f and g are differentiable. Both f and g are differentiable. Okay. What is the derivative of h? That is the question we should ask. One asks. This is that leads to what are called chain rules. Chain rule means taking the derivative in a chain one after other. What is the derivative of y? Derivative of the function y in this case. So the trick is the following. So let us follow the trick. Set z equal to x cube. Therefore, y is equal to sine of z. So it is a function of z, right. So if I now take the derivative, if you know the chain rule, so what you do, you do so now you know how to take a derivative with respect to z, and then if you take a derivative of z with respect to x, you get a derivative of y with respect to x. This is something known to you when you had started talking about derivative of one variables or just the rules of differentiation that we have learned in calculus of one variable. This is known to you. So, what we do? We first take the derivative of y with respect to z and multiply it with the derivative of z with respect to x, and that gives me the derivative of y with respect to x. So, in this case dy dz is cosine of z and dz dx is 3x square. Now, but you know that z is nothing but x cube, z is nothing but x cube. So, then you put in place of z x cube. So, it will be 3x square into cosine of x cube, and that is giving me dy of dx, dy of dx. This is the standard chain rule, and you know this standard chain rule. But what happens if I have a scenario like this, that my z is a function of two variables x and y are real variables, while x is function of some t and y is psi of t, not the same function. Now, if you look at this, you ultimately know that z can be expressed as a function of one real variable, because I can write z as function of psi t, phi t and psi t. So, this is finally a function of t. How? Because define a function theta, define theta from r to r2 such that theta t is by definition phi t psi t. So, I have taken a variable t, but t is in r, of course, t is a real variable. So, I have taken a variable t in r and mapped it to two numbers which are given by phi t and psi t. So, I take t and put them in one function phi, another function psi, and get the two numbers and put them as a coordinate, and that I call as a function theta t. So, z actually can be expressed as a composition of f with the function theta. So, z is f compose theta, but here what happens, theta is carrying r to r2, right, and f is carrying r2 back to r. So, f is a function obviously from where x and y are real variables, r cross r to r. So, ultimately f compose theta, which is z, is carrying r back to r. So, now we can now ask the question, what is dz dt, because this is a function of t. So, in that sense z of t is f composed theta of t. So, if I want to play with this chain rule here, so if I write, for example, say h is, so what did I do? If I write, for example, h is f compose g, so what I actually do, when f and g are functions from real f functions from r to r, then h dash of x is nothing but f dash of gx, f dash of z is your gx here, x cube is your gx into g dash of x. This is actually the chain rule if I write it in this dashed format of derivative. That is, this is same as this is nothing but dy dz evaluated at z, and z is nothing but your gx here, and g dash x is x cube which is gx. I can write gx instead of z, and then this is what you do, dz dx is nothing but g dash x. So, we can write it like this. So, I can imitate this in this case. Now, I have f and I am assuming that f is differentiable, f is a differential function. So, it has the gradient is the derivative. So, let me assume that f and theta both are differentiable functions, f and theta are differentiable. So, for f I have the gradient, and for theta t I have theta dot t or theta dash t, if you want to write in terms of dash theta dash t, and you know what is theta dash t. Theta dash t is nothing but the derivative of phi t and psi t. This way of taking derivative of vectors that we had learned when we had shown how we can study mechanics using function of more than one variables. When we had seen a little bit about computing derivatives and velocities of particles in mechanics, this is what we finally had. Now, what to do? So, this is what I have, and then once I have this, so I will go back and try to write, it in this format. So, I will write z dash t is gradient of f at this point theta, that is gradient of f at phi and psi, which is x and y basically. This dot product, so instead of multiplication I will have a dot product. So, basically I can write, if you want to imitate this, the one here, if you want to imitate this and put it in higher dimensions. So, we are not doing a direct detailed proof, but we are using our intuitive idea to bring what we know in one dimension to higher dimension. That is exactly what we did for the definition of the derivative. So, here I will do the grad f of theta t, instead of multiplication I will have a dot product into theta dash t. So, I know that grad f of theta t can be written as phi t psi t dot phi dash t and psi dash t. You can write dot also, t often refers time, but in this case we are not mentioning, so we are putting a dash instead of a dot. So, what is this? This is x and this is y. So, it is, so instead of multiplication I am using the dot product of the vectors, grad f x y dot phi t dot psi. So, what do I have? I have del f del x, right, del f del x phi dash t, just adding the dot product, del f del y is the gradient, this is nothing but the gradient, del f del x del f del y into psi dash t. But what is psi dash t? Psi is actually x, so I can write this as del f del x dx dt plus del f del y dy dt, because psi is y basically. So, this is your z dash t, and voila, just using our basic idea, this fact this idea we had got by replacing multiplication with dot product, we have got our chain rule for functions of this form. Okay. Now we will go into some other type of composition. This is not the only type of composition available for functions of more than one variable. So, if I am talking about some other kind of composition, let us see, but the same idea would be repeated, the same idea will intuitively put up and do the operations. It could be a Jacobian instead of a gradient, and then when you have a Jacobian we have matrix multiplication instead of dot product and all kinds of such things. But once you can pull in your intuition. It is very important in mathematics to look at things and intuitively, in many cases it happens, every time intuition does not work. Please understand, in every part of mathematics intuition does not work. For example, there is a important part of mathematics called topology where your intuition will fail you many of the times. But here in calculus its subject has itself has been developed as an intuitive one. Do not think that everything in calculus was proved in day one. For example, when you learn about negative binomial in school, you are told, okay, within this range this negative binomial, same if you put x is in this range, there is 1 plus x to the power minus 1 or 1 minus x to the power minus 1. It only makes sense when say x is between minus 1 and plus 1 and all this kind of stuff. But when Newton wrote down the negative binomial, he just wrote down the coefficients absolutely from intuition, there was no proof, and most of the proofs in Newton's Principia comes not using calculus, but it comes using synthetic geometry, Euclid's geometry. So that point has to be kept in mind, that in calculus we can achieve a lot of things, we can make a lot of advancement by very careful intuitive thinking. Can you say that, okay, is intuitive thinking careful? Of course, in intuitive thinking you can make very big leaps in the imagination, but that does not mean that that leap can be thought out carefully. So here we are doing that kind of leap to give you the chain rule. When I was a student, I can tell my own experience is that these kind of leaps that you can make in the imagination are not told. We are told this is a formula, memorize it, and that is the thing that I want to take you out of. Once you understand what is the meaning of the chain rule in one dimension, which is exactly this. For example, here z can be written as gx. If you are not comfortable, I am writing as gx. So del z del x is same as del g del x. Okay. So del y del z is same as del y del z or del y del g, right. Now once you know this form, what do you have? Once you know this form, you can use this form to get things for higher dimension. So once this intuition is clear, you do not have to do any rote learning. This is something, so you can look at the problem, you can easily create the chain rule sitting there. You do not have to do rote learning. The whole purpose of this course and also my course in function of one real variable has been to take you out of this rote learning of mathematics. That you can, with your intuition, if you do not always want to get into the rigorous proof at the very first hand, I think it is not advisable to get into rigorous proof at the very first place, because rigor sometimes causes rigor mortis. So I do not want that to be done. It might kill the fun of the subject. Once you can from your intuition go from one concept to another and you see that the concept actually works, that is a huge fun, and I think it is very important to have that fun. So now let me go to something higher, something different, some different kind of chain rule. Okay. Now here my chain rule number 1, here maybe I will call it chain rule 1. So next I will give chain rule 2, I will give you a problem, I will set it up as a problem and let us see, let us discuss how we will go about it. Chain rule 2. So what is this chain rule 2? So here I have function f which is from say R2 to R. See what I am doing from R2 to R, I am keeping the whole thing within R2 just for your comfort. you can actually take it to Rn, you can actually take it to R3, but once you learn in R2, you can actually extend it to R3 Rn as you feel right. We can go up to R3 as an example. So, a function f is from R2 to R and another function g is given from R2 to R2. F is expressed in terms of uv, these are real variables. And g of xy, so xy is an element of R2, is expressed as u of xy and v of xy. So, now we construct the function h of xy. So, if f is carrying R2 to R, if g is carrying R2 to R2 and f is carrying R2 to R, then h, which is the composition of f and g, it carries R2 to R. So, g of xy is first operated by g, that is f composed g of xy. So, this can be written as f of g of xy and can then be written as f of, because g of xy is u of xy v of xy. My question now is h, what is h? H is a function from R2 to R. So, it is a function in higher dimension, not R to R. For R2 to R, we need to compute the gradient. For a function from R2 to R, we need to compute the gradient. Assuming that h is differentiable, there is a gradient of partial derivatives. So, basically I am asking you what is grad of. So, basically h is expressed in terms of f and g, which are also differentiable. So, now I am asking you that can in terms of the derivatives of f and g, you can compute the gradient of or the derivative of h, and what is the answer? So, write again the derivative of h is a derivative of f in terms of u and v, that is a gradient of f in terms of u and v, because f is from u to v, multiplied by, now g is a function from R2 to R2, so it is a function from Rn to Rn types function, vector valued function of a vector, vector is been carried to a vector. In that case we compute Jacobian matrices. So, here we have to be very careful, here we compute the Jacobian matrix, this into Jacobian of g computed at xy. So, what is this grad uv? This is nothing but g. So, f grad f of g computed at xy into the multiplied with the Jacobian matrix of xy. This is the chain rule. Now, we will elaborate on the chain rule. In the next page, we will elaborate on the chain rule and we will write down the chain rule in details. So, you see we are taking the same law, same chain rule for derivatives, and by intuition we are just coming up to this. The same story we are repeating, but we are putting in the correct form of the derivative as the functions are. And this is very important, that we are absolutely using intuition. We have not gone into rigorous proof, and in this case I will not go into any rigorous proof. Of course, everything can be proved very rigorously using the limits and all those things, fully using the derivative definitions, but we are not going to get into rigorous proof under any circumstances. Here in this case we will not get into rigorous proofs, we will get into intuition. That is what I want to teach in this course and had been trying to teach in my course on calculus of one real variables. I never thought that I will do courses in calculus, but I am really doing it. But when I am doing it, I am trying to again and again stress that you can use your intuition to move from one dimension to the other by really filling up the same story with the appropriate objects. That is it. So, we had written, let us again write, grad of hxy is grad of fuv into Jacobian of gx of y. So, let me do the computation here. So, grad of h of xy is del h del x, all evaluated at a given point where you are computing, of course, del h del y. So, these are two components. Here I have del f del u, del f del v, and now I am multiplying by the Jacobian matrix. So, what is the Jacobian matrix of G? The Jacobian matrix is a function from R to R, R2 to R2. So, it is a 2 cross 2 matrix. So, we will take the gradient of G, in this case u and v. So, G is from gxy is uxy vxy. So, the Jacobian matrix, first I will take the gradient of u and put it in the first row. I will write the gradient as a row vector. So, I will do del u del x and del u del y, and then I will do the second thing. I will take the second function v and compute its gradient and put it as a row vector, del v del x del v del y. Okay. Now, I will do matrix multiplication. So, here it is a 1 cross 2 matrix, which is a vector, row vector. Here it is a 2 cross 2 matrix, and that will give me finally a 1 cross 2 matrix, which is a vector, and that is exactly same as del h del x del h del y. So, let me do the multiplication. So, how do I do the multiplication? Take this and multiply with the first row, right, and take this multiplied by the second row. So, I will have del h del x into del h del y. So, how do I get my first one row? So, I will take the first row of this matrix, it is one row, multiply with dot product with the first column of this matrix, the Jacobian matrix, and then I will take the, for the first entry in the first row, for the second entry I will take the first row and multiply with the second column of the Jacobian matrix, that is matrix multiplication. So, I will have del f del u del u del x plus del f del v into del v del x, and the second entry is again to begin with is del f del u into del u del y plus del f del v into del v del y. So, which means del h del x is equal to this part, this del h del x is this part. So, this part that we have obtained, the first component of the right hand side is del h del x, second component of the right hand side is del h del y. So, I can now write del h del x is now del f del u into del u del x plus del f del v into del v del x. This is what I have as del h del x. Similarly, I can now write down del H del y is equal to del F del u into del u del y plus del F del v into del v del y. So, here we clearly were able to compute the partial derivatives of H, which is giving us the gradient or the derivative in this case. So, you see how beautifully and simply this rule has been now brought over to this case, to the higher case, and that is what I want to stress on, that you can actually do the thing in such a neat and simple way. And that is what we really have to look into the whole thing, that just by intuitional pickup we can get such neat clean results. I will leave you to have fun. What is the fun is, I will not do anything, I will give you two situations, and in these two situations you have to figure out how to write the chain rule. This would be, you can write down, you can check it up with the forum, or you can ask us, we will give the answer. Give them as homework. So, this is what you have to do before you check on with anything else. So, F is now from R3 to R, we have just made it look little more fearful for you, but I am going to tell you just increasing one more component, nothing else, it is just fun, you can check it out. F is from R3 to R and G is from R2 to R3 instead of R2 to. So, G, so F is written as a function of variables, so Z equal to U V W. So, this constitute element in R3, and G is written as follows, G x y picks up an element in R2 and puts it in R3, which is U of x y, V of x y and W of x y. Now, H x y is equal to F composed G of x y. So, what is happening here? Here H is being carried from R2 to R. So, G is carrying from R2 to R3 and F is carrying one from R3 to R. So, H is being carried from R2, H is been carried from R2 to R. So, H is finally bracket a function from R2 to R. My question of course is compute grad Hxy, basically get the chain rule, that is get the chain rule. That is compute grad Hxy in terms of the derivatives of f and g, get the chain rule. I can make the problem little more harder by writing f is from R3 to R and g is from R3 to R3, okay. So, f is from R3 to R, but g is from R3 to R3. So, g will become x y function of x y z. So, g will be g of x y z, u of x y z, v of x y z, w of x y z, and grad would be h would be h of x y z. So, it will be R3 to R, h would be a function from R3 to R, then you can get the chain rule. You can keep and make it much more complex and complex and complex, but just for homework do this, and I am requesting you please try this just in the way I just worked all these things out, just the one I worked out before. Please do this. So, with this I end my discussion today. I hope you enjoyed it. I still want to show you this neat simple work, and I would rather appreciate your comments on this lecture, and if there is anything you can definitely ask us, and I close the class today. Thank you and have a nice day.